seminar series. So today we're going to have two talks on new Hooft anomalies and phases of gauge theories. We will record also the meeting that you can find on YouTube later. And our first speaker is Erich Poppitz.
Okay, thank you for inviting me. Thank you very much. Let me share my screen. There we go. You should be able to see it. I hope you see my cursor too.
Yes.
So this is a talk about new Hooft anomalies and phases of gauge theories. The goal of this talk is to give an informal intro to non-experts. So I saw that there are a few extra experts in the audience, so they will be bored, but they chose to be here, so whatever. They can keep me honest. So this is the goal. It will be very simple-minded. And my goal is also to give a few examples of what these anomalies do for us. And most of the work that I've been talking about is done with Mohammed Tander and on one occasion with Thomas Ritov. Oops. In general, one issue that we are concerned with when we study quantum field theory is the renormalization group flow. So if you have a theory which in the UV is at some fixed point, usually asymptotically free and weakly coupled, studying the infrared of this theory is a challenging task because of strong coupling. And anomaly matching is one of the few rigorous handles that we have on the renormalization group flow. So some set of number computed in the UV has to be matched by whatever fantasy you may have about the infrared. So it is constraining. Just a reminder on Hooft anomalies for those of you who have not thought about it lately. Consider a QCD with 3 colors and 2 massless flavor fundamental quarks. The global symmetry is the usual one, the chiral SU2 left cross SU2 right cross the baryon number. And those are exact symmetries of the theory. These Hooft anomalies arise when we attempt to gauge these symmetries. So we introduce background gauge fields, and we find that gauge invariance for those background fields is violated. For example, if we do this for the baryon number and SU2 left, we will find that there is a mixed anomaly given by this usual triangle diagram. The baryon number is anomalous in an SU2 left background. And the coefficient of that diagram appropriately defined is renormalization group invariant, and it has to be matched by whatever infrared physics occurs. It's easy to see that if you have a single baryon doublet of SU2 left with baryon charge 1, it precisely matches this because here there are 3 quarks running because the color is SU3, but the charge is 1/3. Here there is 1 doublet and the charge is 1, so the matching is perfect, or it can be matched by massless goldstones as well. In any case, the presence of this anomaly implies that the infrared physics is non-trivial. So as I was growing up, physics-wise in the 1990s, I thought that anomaly matching was set in stone. So I thought that everything was figured out after the paper of Hooft and a few other papers, important papers that followed. And this zero form or traditional anomaly matching played a very major role in many developments in quantum field theory or model building, if you wish. For example, in Preon models of compositeness, Hooft anomaly matching was one of the exact few tools available. And in the study of Zyberg dualities, of course, it was a major tool. So to me, at least personally, in 2014 and a few years later, which it took for this to soak in, the realization by Gayotto and collaborators that there are anomaly matching conditions that have been really missed before, which I call generalized Hooft anomaly matching, that came as a revelation. So it's a very exciting development, which brings new tools to study renormalization group flows. So my definition of generalized Hooft anomaly matching, it really applies mostly to the stuff I study. And roughly speaking, it will boil down to the following, because I will try to explain. So we'll consider theories that have exact global discrete symmetries. And we will see that there are anomalies. These symmetries become anomalous after particular background field for various global symmetries are turned on. But these are background gauge fields which are turned on in a sort of a smart way, in a way compatible with the faithful action of all the global symmetries. In some cases, these backgrounds can be interpreted as gauging higher form symmetries. So I will try to explain on an example how this works. Currently, this is a very active area of research across many fields: condensed matter, mathematical physics, high energy theory. So there is a lot of stuff going on, and there is impossible to review. I come from the high-energy theory end of things, and the way I study things usually is by means of an example, and I study the dynamical implications. I should also say that the references in my talk are a little bit scattered. I have not referenced everybody that I should have, but you can find a lot better reference list in the papers. So as I said, I will learn by example, and what we will study here is vector-like theories. Okay, so Ken will talk later about interesting work about chiral theories. So the class of theories I will study are SUN gauge theory with NF Dirac flavors of fermions in some representation of anality NC. So instead of using Dirac flavor, I will use the two Weyl components in complex conjugate representations. Just a reminder, this anality is 1 for the fundamental, 2 for the two index symmetric or anti-symmetric, and n for the adjoint. The global symmetry of that theory, this part is very similar to QCD. There is some chiral symmetry left, right, there is a baryon number, but there is something which is slightly distinct from QCD, and that is the fact that the axial U1 has an anomaly-free discrete subgroup. So you take the U1 axial, it acts on the psi and the psi tilde with the same phase. The mnemonic is that the mass term has to be violating the axial symmetry, and the mass term is written like this in this notation. So under a U1 transformation, the measure changes according to Fujikawa, by the following factor, So this is the infinitesimal U1 parameter, NF is the number of flavors, 2 is because there is two Weyl fermions, T is the Dynkin index of the representation, and Q topological is the topological charge of the background gauge field. And what we see is that this is not an invariance of the measure of the theory, unless alpha is quantized, and it has to be quantized in units of 2 pi over 2 NF T. And so U1 is broken by the anomaly to this discrete subgroup 2 NF TR. I should just mention that in QCD, TF is 1. In my normalization, TF is the fundamental. This symmetry is part of the baryon number and the centers of SU2 left and SU2 right, so it's not an independent symmetry. Again, the moral now is that this anomaly-free discrete chiral symmetry transforms the measure of the partition function by a phase e to the I2 pi times the topological charge, and because topological charge is quantized, that is an invariance, an exact symmetry of the theory. Okay, so that symmetry will play an important role. In addition to this symmetry, there is a new kind of symmetry known as a one-form symmetry. And this symmetry is denoted here by 1, meaning that it's a one form. I'll say in a moment what this means. And the rank of this cyclic group is the greatest common divisor between the number of colors and the anality. So instead of doing number theory, it's best to consider an example. If you consider the theory with adjoints, the greatest common divisor is n, so that there is a Zn one-form symmetry. Physically, what this means is that fundamental quark props cannot be screened in the adjoint theory, just like they cannot be screened in the pure glue theory. And the fact that there is a one-form Zn symmetry means that n fundamental quarks can be screened. That is to say, fundamental strings are unbreakable and their number is conserved mod n. Similarly, for the anti-symmetric or symmetric theory with even n, P is 2, the GCD is 2, and there is a Z2 one-form symmetry, which means that fundamental quark probes cannot be screened in that theory if the number of colors is even. And the Z2 symmetry means that strings are unbreakable, but their number is only conserved mod 2. 2 fundamental quarks can be screened. That's pretty obvious, actually. So this one-form global symmetry acts on topologically non-trivial line operators, Wilson loops that wind around the world, say around the torus. And it has been used before as a classic prop of deconfinement, which is not something that's particularly interesting to me at the moment. And so the global symmetry of the theory is this. There are some discrete identifications which eliminate redundancies, which are important, as will become clear later. I will not discuss them in detail, but really this is, for example, the fact that U1b and the center of these flavor groups have something in common, etc. What I want to stress is now the definition I gave of these generalized anomalies, that I will be turning some background fields for global symmetry, and I will find that there is an anomaly of the discrete symmetry. So the idea of these new anomalies in the incarnation that I'm discussing, it goes like this. So let's put the theory on some large manifold, for example, a 4 torus, or later, well, I will not discuss that in detail, but it may be advantageous to consider another manifold like CP2. So we want this manifold to have some scale so that we can change the size and we can take the infinite volume limit. So when we put the theory in this large manifold, we can turn on judiciously chosen general global symmetry background. So we turn on backgrounds for this global symmetry, and these backgrounds can be such that they can have non-integer topological charge, and if this topological charge is non-integer, then the discrete chiral transformation, which changes the partition function, as I told you, like that, will not be a symmetry anymore, because if Q is not an integer, that's not a symmetry. So the function will change by some phase, typically some ZK phase, depending on the situation. So this phase is the mixed anomaly between the discrete chiral symmetry and this global background for the global symmetry. This phase can be argued to be a normalization group invariant in various ways. One way is to argue that it's not a variation of a local four-dimensional term. Another way is to develop a variation of the Hooft spectator argument. So the point is that this phase has to be reproduced by the variation, by the theory at any scale. In particular, in the deep infrared, it has to be reproduced. And if the theory has a unique vacuum with a mass gap, there is nothing that can reproduce this phase. So this means that something has to be there in the infrared to give rise to this phase. So there remain 2 points to discuss during the rest of my talk, in the limited time I have. The first point I want to bring across is to what are these backgrounds that have non-integer topological charge. And I don't assume that this is known by everybody, so I will try to give a brief discussion of what these backgrounds are, which is hopefully understandable to the larger community. So I will discuss what these backgrounds are, and then I will discuss examples of what constraints this new anomalies place. So usually they require that this discrete chiral symmetry be broken or partially broken. Of course, it is believed that if the theory in the infrared is a CFT, these anomalies should be matched somehow, even though maybe the detail is not understood. They constrain the physics of domain walls. I won't have time to talk about that. They limit or forbid scenarios where the massless composites saturate all the usual traditional Hooft anomalies, as we know. They also constrain finite temperature phases. For example, they limit the ordering of various phase transitions as you change the temperature. They constrain the physics of finite T interfaces, etc. So I will discuss examples of the first and the third thing, and I cannot discuss the rest. I want to mention immediately a disclaimer. These generalized anomalies, just like any anomaly matching condition, do not tell us which consistent infrared scenario is realized. So they just can forbid various options. And I think in general it's true that we do not yet know, or let me say I do not yet know, what is the complete set of consistency requirements that one should impose. So let me start with the first point. The first point is to explain what these backgrounds are. And these are known as Hooft fluxes and their generalizations on various manifolds. So what all these manifolds have in common is that they have various non-contractible loops or non-contractible two cycles. And in general, as you remember from general relativity, for example, you cannot describe these manifolds using a single coordinate chart. So imagine that you have two coordinate charts, I and j, like this, and there are gauge fields in each of those charts labeled by AI or AJ. And on the intersection of the two charts, they are related by a gauge transformation. So this is a matrix in SUN, and it's known as a transition function. It's a group element. And it makes sense that if you have three such overlapping charts, if you, in the intersection of the three charts, you can describe the physics using whichever field you do. But if you go from describing with the I chart to the L chart to the J chart and then back to the I chart, you should be consistent. So on triple overlaps, these transition functions should have a product equal to 1. And so if you formulate the theory on a generic manifold, the path integral is an integral over all gauge field configurations in the various patches and over all these so-called transition functions obeying the co-cycle conditions modulo gauge transformation. So that's a sort of a formal formulation of a gauge theory on this background. Now, what's interesting is that this is a way to reveal the presence of this one-form symmetry. So the formulation in terms of patches and these data, the gauge fields in every patch and the transition function between patches, it's pretty obvious that it's invariant under the following transformation. You take the transition function on a given patch and multiply by a Zn phase. And the particular element on Zn depends on, you choose it different for every patch. And this is an invariance of this, provided these numbers M obey this condition, which is sort of a co-cycle condition for them on the triple overlap. That's pretty obvious that this is a invariance of this. So this is actually a global symmetry of the theory, right? It's a symmetry of the dynamical variable, and it's a strange symmetry. It doesn't act on closed Wilson loops, but it only acts on winding Wilson loops around the world. And it doesn't act on the gauge field, you can see, right? It only acts on the transition functions. Just to see, to get an idea about that, consider a contractible loop like this that goes from the I patch to the J patch to the L patch. And if you want to write it down, you write the path-ordered integral in the region I using the I field. In the region J, you use the J field. In the region L, you use the L field. But to make this gauge invariant, you have to insert these transition functions when you transition from one patch to the other at these points 1, 2, and 3. And then this is a closed Wilson loop, and it's pretty clear that it's invariant under this transformation because of this condition on the Zn elements. On the other hand, if you have a non-contractible loop, for example, imagine that space-time is a circle times a non-compact space, then you can cover that with one patch, but the gauge field on the left and on the right in general will be related by a gauge transformation, just like going from patch to patch. And and then if you want to write a gauge invariant Wilson loop, you have to insert this transition function in the trace using the Wilson loop going from here to here. And it's pretty clear that this transformation now on the non-contractible loop will act by a Zn phase. So this is the global symmetry, and this is how it acts. The only objects it acts on are non-contractible loops. And we can introduce backgrounds to this symmetry. Okay, this is sounds maybe somewhat strange, but introducing a background for this symmetry means that we consider transition functions and backgrounds such that this co-cycle condition is relaxed. So on triple overlap, we say that these transition functions do not give one, but they give rise to some Zn phase. And if you want to consider gauge transformations, these numbers n then change in the following way under the Zn transformation when you relax the condition that these m's sum to 0. So this can actually become quite formal. And there is different formalisms to describe this. For example, I think Ken will use a continuum formalism using a two-form Zn gauge field. It is actually closely related to these numbers of on triple overlaps. So I have no time to describe that. Instead, I want to describe something significantly less abstract. And that is to say, I want to describe two fluxes as examples of backgrounds which correspond to gauging this one-form symmetry. That will be important for us. So, let's consider a simple example. Consider a 4 torus of size L. So L is the size of the torus. And the 4 torus is a torus in x1, x2, x3, and x4. So let us consider just a section of that torus in the 1-2 plane. And we can consider the torus as just one coordinate chart, so a square, with the edges identified, but the gauge fields on opposite edges don't have to be the same. They can be related by a gauge transformation. And I have chosen here an example where the only non-trivial transition function is the one relating the field on the bottom to the field on the top. The field on the left and on the right I have taken to be the same. And let us consider the following example of a gauge background. So the gauge field only has a non-zero component in the one direction, depending on x2, and this is the particular configuration of the gauge field. This is just a particular choice of Cartan generator. What is interesting about this gauge field, which is not periodic, you can see right away that if you change x2 by L, this field changes by a gauge transformation, which is abelian, so you can write it like that. And this gauge transformation is given by this element. So it's pretty clear that if you change x2 by L, this changes by a constant 2 pi over L times this generator, and that's precisely what's written here. So this gauge transformation is my transition function here. And what you see is that this transition function is not a periodic function of x1. So the transition function on the top, which relates the top to the bottom, is a function of x1, of course. It's defined on the overlap. And it's not periodic. And the fact that this is not periodic is essentially equivalent to the fact that we gave up on the co-cycle condition. So this means that such transition functions are not allowed in the SUN theory. They correspond to putting backgrounds which correspond to gauging the one-form symmetry. And this thing is known as a Hooft flux in the 1-2 plane. It's independent on x3 and x4, and it has a constant flux 1-2, F12, as is pretty easy to see. Okay, so we can do the same thing in the 3 and 4 direction. Okay, and then we'll get an F34, which will be identical. Okay, and having F12 and F34, we can compute the topological charge. I'm not going to do the computation, but because of this 1/n factors, we find that this topological charge is not an integer. In fact, it's exactly 1 minus 1/n. But remember, I told you, for example, that in the adjoint theory, there was an exact chiral symmetry, which is this Z2 number of Weyl fermions times the number of colors. And so that was an exact symmetry because the topological charge of the SUN gauge fields was integer. But now we gauge this one-form symmetry, and what we find is that the topological charge is not an integer anymore. So this ceases to be a symmetry. So there is some Zn phase in the transformation of the partition function, which is the mixed anomaly between the chiral symmetry and this, in this case, center symmetry background. And then the idea is that we can put both the UV and candidate IR theories on T4 in the same global symmetry background. And then both of them should reproduce this phase of the partition function. So this is an example of such a background for the adjoint theory. But now, as I said, we are going to also consider fields of non-zero anality. So if you have a fermion field of non-zero anality, you also define it in different patches, and the field in the ith and in the jth patch is related by partition function for all the backgrounds. So for the color, the transition function of the matter field is some product of the partition functions for the gauge field depending on the representation. Only the anality matters. So I have written here the transition function to the power of the anality. Of course, there are transition functions for flavor and baryon backgrounds if you introduce such backgrounds. And it's pretty clear that for a field with non-zero anality, this sort of transition function is not allowed, because what this means is that the field, the matter field, will not be single valued on the torus. For example, if you consider relate the matter field at this point, and at this point, and consider the matter field relate starting from this point, relating it to this point, at this point, you will find that it's not single valued. So this is not good for fields of non-zero analities. However, you can do the following trick. You can introduce backgrounds for the flavor and the baryon, which cancel this Zn phase. So this is a very explicit example. Consider a background for the baryon field, which has this shape. It is also not periodic. So it is also not periodic. It has a transition function, which looks like that. It's very easy to see. And this transition function is not periodic up to a factor of e to the minus I 2 pi the anality over the number of colors. So this transition function is not periodic. This transition function is not periodic, but this product is periodic, so the field is single valued. Okay, so for a field of a non-zero anality, you can compensate by introducing fluxes for the baryon number and the flavor. I should have stressed that for the adjoint field, this phase doesn't matter because it cancels, right? There is omega dagger and omega, the way the representation goes, okay? So it's possible to introduce such fluxes for the flavor, the baryon number as well. And just like we did the calculation for the topological charge for the color gauge field, we can do the same calculation for the flavor and the baryon topological charges. So this calculation, I explained how it's done. You can turn on backgrounds for the flavor. You can turn backgrounds for the baryon number so that the various phases correspond to each other. And there are these fractional topological charges. And again, the idea is that you can study both the UV and the IR theories. You can put them on T4 in the same global symmetry background. And if you put them in a global symmetry background, there will be an anomaly because all these charges are fractional. And that anomaly should match between the UV and the IR. Oops. Okay, so this was the story on T4. It turns out that large classes of theories can also be formulated on non-spin manifolds. And I will not discuss details of that, but the only point I want to make is that on non-spin manifolds, the phases that you obtain are more constraining because some topological charges get quantized with an extra factor of 1/2. So if you just compare, for example, this one to this one, you see that there is more constraining phases. So let's go back to our theories. So we have our theories. This is the global symmetry. So I consider the theory on T4 or CP2, and I consider the discrete chiral symmetry of that theory. And I put this non-trivial background that have non-integer charges. And these backgrounds, right, and I compute the variation of the partition function as a discrete chiral symmetry. And this is what I find. And this is just using very simple Fujikawa arguments, right? You just, if you know the topological charges, you can compute the phase in the partition function. So this phase in the partition function, the mixed anomaly between the chiral symmetry and this non-trivial background is this. And it should be matched in the infrared. So for lack of better name, we call this the BCF anomaly, baryon cover flavor anomaly of the chiral symmetry. And it has to be reproduced by the theory at any scale. And so now you can play games. So this is the result for the phase computed in the UV. It has to be produced in the IR. So you can do your exercise in number theory. I put quotation marks because we do number theory by the computer. We don't prove things. And you can prove the following statement. Suppose you have found a set of massless composite fermions which matches all the traditional zero form anomalies. So by zero form, I mean the anomalies involving only the zero form symmetries. And then you demand that this new phase in the transformation of the partition function be matched in the infrared by this set of fermions alone. And then you can show, just using you find some conditions involving some integers, and you ask where do these integers exist. And then you can show that by themselves, these fermions can not match the new anomaly if the greatest common divisor of the number of colors and number of flavors is bigger than 1, or the greatest common divisor of the number of flavors and anality is bigger than 1. Otherwise, they do match the anomaly. So this sort of argument, in cases where these conditions are hold, means that massless composites at the sole player in the IR are ruled out. Okay, so typically this means that you need something else to happen in the infrared. Typically symmetry breaking, associated domain walls, or some TQFTs. And I will give examples, and I think I will limit myself to one example because I have the feeling that time is short. So let us consider the following theory. Consider QCD adjoint, so QCD with adjoint fermions, say with gauge group SU2, and consider one Dirac flavor, that is to say 2 Val fermions. Okay, so a theory with 2 Val fermions and gauge group SU2, it has an SU2 flavor symmetry rotating the 2 Val fermions. And there could be a phase where SU2 flavor is broken down to SO2. And the anomaly applications in the IR for this theory were studied in this paper. But there is also another phase that one could contemplate. And this is a phase where there is a massless composite Dirac fermion, which is a doublet of SU2. So it looks like this. I didn't write all the indices, I'm sorry, but you can write out of these 2 Val fields an invariant, which is an SU2 flavor doublet. And it matches all the traditional zero form anomalies. And you may ask why we consider that thing. And we considered it for the following reason. This is a theory which can be solved if you consider not R4, but R3 cross S1. And this was done by Unsal in 2007. And that is precisely the spectrum that occurs in that theory. So we were surprised that this actually matched the continuous anomalies on R4 as well. But this theory has a GCD of n and the finality, which is n, which is bigger than 1. So it should not be that this fermion alone saturates all anomalies, as I argued from our theorem from the previous page. And it's also pretty clear that it cannot match all anomalies because the backgrounds we introduced gauge the center symmetry. And this gauge singlet Dirac fermion, it's really a Dirac fermion, which is an SU2F doublet, or 2 Val fermions. Okay, so these 2 Val fermions, they don't couple to the center symmetry. So there is no way that the infrared can match the center symmetry. But it turns out that if you have partial breaking of Z8 to Z4, so Z8 is the chiral symmetry here, to Z8 to Z4, due to some 4 Fermi condensate, which is an SU2F singlet, then the anomaly can be matched on T4 using T4 backgrounds. And again, this is interesting from the point of view of the solution on R3 cross S1, in the sense that this is exactly the symmetry realization which occurs when you consider the theory on R3 cross S1. And now comes the new development, and this is the fact that you can consider this theory on a non-spin manifold. And then it turns out that on CP2, the unbroken part of Z4 chiral symmetry cannot be matched. It turns out that there is a Z2 valued anomaly. So you do need something else in the infrared. And it was proposed that that something else is a Z2 topological field theory, which only activates in non-spin backgrounds, which matches the anomaly of this unbroken symmetry. So this has been studied by various people in this language that I described. This was described in our last paper with Mohammed Amber. So this theory has been of interest for various people, including Mesmer people of all things, for their own reasons. So we have this two scenario which appear consistent. Of course, as far as the scenario B, the strongest point of support of that scenario is the fact that it is realized in R3 cross S1. I will not speculate what happens on R4. This is not something that anomaly matching can tell you alone. There are lattice studies in the groups of Vienna at MIT, which actually are studying the behavior of that theory, and the latest summary is in this paper. So this illustrates the utility of the new anomaly matching. So they are more constraining than the traditional ones, which is what I already said before. How many minutes do I have?
In principle, we are at the end. How much do you need?
Okay, I can actually.
5 minutes you can take, but
I can actually. Okay, not more than 5 minutes. Okay, so the two other examples I have chosen are actually, they have very similar flavor. With Thomas Ritov, we proposed a somewhat, maybe crazy realization of symmetries and anomalies for a generalization of that theory. So you take QCD adjoint with a larger number of flavors, and the story is very similar. As a matter of fact, you can have a gauge invariant copy of all these UV fermions, which match all the traditional anomalies. You need some discrete symmetry breaking to match the new anomalies, which can be done using some multi-fermion condensate. Again, this is what happens on R3 cross S1. Let's not discuss that. Again, we have two scenarios which anomaly matching alone cannot tell you what's happening. And my final example is this theory with antisymmetric tensors. For example, for simplicity, just take SU6 with a single Dirac antisymmetric tensor. This theory has a Z8 chiral symmetry. And of course, one possibility is that there is a bilinear fermion condensate which breaks Z8 to Z2. Then there is domain walls with non-trivial physics and some interesting stuff, but that's not something that I can talk about in great detail. But it's also interesting that there is a relatively simple massless composite Dirac spectrum. As a matter of fact, it's just a single massless Dirac fermion that saturates all the traditional zero form anomalies. The new anomalies required that the Z8 zero chiral symmetry be broken to Z4. And again, on CP2, there is some anomaly, which you can see by, for example, turning on B flux, and something else is needed in the infrared. And it has been argued to exist in these recent papers. These are my examples. I will not give you other examples. So let me just conclude and give the baton to Ken. I think these new Hooft anomalies are very interesting. They give us a new handle on non-perturbative infrared dynamics. They do place interesting constraints on the infrared physics. I showed you in these vector-like, QCD-like generalizations with discrete chiral symmetries that they usually require that the symmetries be broken or partially broken. In fact, there are some general results about that recently. They also limit or forbid scenarios where massless composites saturate all the usual Hooft anomalies. And I didn't talk about the fact that they constrain the physics of domain walls or constrain finite temperature phases, but that has been studied. There is literature on that. And again, generalized anomalies do not tell us which phase is realized. That needs some other input. But maybe if there is more and more consistency requirement that one can discover, one can further narrow down the possibilities. So that's my story.
Thank you very much for the very clear talk. So we have some time for questions. I see a lot of experts in the audience, so just ask.
Too clear.
So
Hi.
Okay, go ahead.
Yes, it's a very nice talk. Can I ask something very simple?
Yeah.
So my question is like, is it correct that these new talk anomalies only exist when the fundamental fermions are in the adjoint or symmetric or anti-symmetric tensor representations on the color, but do not exist for the fundamental representations? Is that correct?
So I considered anomalies of the discrete chiral symmetry. Indeed, for the fundamental representation, there is no discrete chiral symmetry, but they exist for the fundamental representation if, for example, you consider CP symmetry. If you make the fermion slightly massive and you consider the theta prime to be pi, then there is a CP symmetry, and there is a mixed anomaly between CP and these backgrounds. So they do exist in theories with fundamentals, but I didn't discuss that. So they would involve CP symmetry, which has to be arranged. Okay, so this is a CP symmetry which requires integrality of the topological charge. So it's a particular point in the phase space of fundamental theories. This has been studied quite a bit by other people.
Okay, thanks.
I have a very naive question. So these P-form symmetries, are they associated in some ways to physical degrees of freedom, like strings, domain walls, or is more formal construction?
You mean the one-form symmetries? Yeah,
Yeah.
they act on confining strings. You can say that. Yeah. As a matter of fact, I kind of said it in the. Well, I didn't make the connection because I had to rush. It's 30 minutes, but do you see my screen, by the way?
Yeah.
Okay, good. So I said that this one-form symmetry means that n fundamental cores can be screened. So they really act on the confining strings, so it's sort of a sourceless confining strings. Okay. So that's the physical interpretation.
So there are symmetries that they only exist in the confined phase.
No, the symmetry is a symmetry. It exists in any phase. But it's really something that acts on non-contractible Wilson loops. Okay, this is the formal way. Okay, in the confining phase, it acts on these flux tubes, but they're created by these non-contractible Wilson loops. It is an honest-to-God symmetry of the theory. Okay, it's just not very usual because it doesn't act on local fields.
Is there any other question? So otherwise, we move to Ken Konishi.